In the last video, we characterized the vector A, the acceleration vector. In this video, I'm going to focus instead on B. B, remember, was just defined as R crossed with V, which we proved was constant. So we've already got one characterization of B right here, because we said if it's always R cross V, then it's R naught cross V naught. It's the initial position crossed with the initial velocity. And that, of course, since we can characterize R naught as just the initial distance times I, and V naught as the initial speed times J, that's going to give us the initial distance times the initial speed times I cross J, which is K. So that characterization I'm going to write up here, that it's just R naught V naught times K. I'm going to now try to get a second characterization of B, using the fact that it's just R crossed with V. Now, if B is R crossed with V, we just saw that we could describe the position vector as R times U. So that's the distance of the planet from the origin, the magnitude of that position vector, times the unit vector that points in the right direction. And we're crossing that with V, but I know that V is the derivative of the position. So I can write this as the derivative of R times U. Now recognize that this is a product right here of a scalar valued function. The distance of the planet from the sun is a scalar valued function, and a vector valued function. The unit vector that points from the sun to the planet is also going to be a function of time, but it's a vector valued function. So I have a version of the product rule that tells me how to take the derivative of a product of a scalar valued function and a vector valued function. So I'm going to use that. I'm going to say that this is, I take the derivative of R with respect to t, so that's just the derivative of the position, of the distance of the planet from the origin, and I multiply that by U. Plus, I take R, that distance, and I multiply that by the derivative of U. Excellent. Now, I've got to take this vector sum and cross it with RU. But I know that I have a distributive property for the cross product. So I can say this is RU crossed with dr by dt copies of U, plus RU crossed with R times the derivative of U. So I've got these two terms. Now if I look at this first term, that's a scalar multiple of U. Now R is a function of t, so it's going to be a different scalar at different moments in time, but that doesn't erase the fact that that's going to be a scalar multiple of U. This is also a scalar multiple of U. Nifty property about the cross product, I can take those scalars and I can just do the cross product first and then multiply by those scalars. So here I can say this is just the product of R and dr by dt being multiplied by the cross product U crossed with U. That's just that first term, but this is 0. If I cross a vector with itself, if I cross a vector with anything parallel to it, I'm always going to get 0. Now, I'm not done. I haven't done the second term yet, but that first term is going to be 0. Now, for this term, I'm going to do something similar. R is a scalar valued function, and R is a scalar valued function, so I'm going to pull those to the front and write that as R squared, and then we're looking at U crossed with the derivative with respect to time of U. So I want to work that out, and I'm going to do that by writing U in terms of theta. Okay, so remember, U, we said, was cosine of theta, sine of theta, 0. Now that's writing U in terms of theta. I want to now calculate the derivative of that with respect to time. So I need to recognize that theta is a function of time. if I'm pointing towards an object that's at different positions at different times, the angle that I make with the x-axis is going to itself be a function of time. So, recognizing that this is a function of time, I can say if I'm taking the derivative of this with respect to time, this is basically just a function composition. I'm going to take the derivative with respect to theta, which would be negative sine theta, and then multiply that by the derivative of theta with respect to time. That's just chain rule. Same thing here. The derivative of sine theta with respect to theta would be cosine of theta, and then we multiply that by the derivative of theta with respect to time. And of course, the derivative of 0 is just going to be 0. Okay. Now, this is the same scalar valued function that shows up in both of these components. And I can actually say, well, it's there too, because 0 is 0 copies of d theta by dt. So if I want to, I can pull out that scalar and say this is just d theta by dt times negative sine theta cosine theta 0. So that's my du by dt here that I need to cross with u. Okay. So let me just clear some space. So what we've determined is that what we're going to end up with is just this last term, because we're adding it to 0. We're going to get r squared copies of u crossed with the derivative with respect to time of u. Okay. So let me just write that up here. And then let's work out what that is. Okay. So I'm going to just focus right now on the cross product. We'll work that out. Once we've got that, we've got to scale it by a factor of r squared. Okay. All right. Now, what we've just said is that this is cosine theta, sine theta, 0. That's our u. Crossed with, this was our du by dt. So it was d theta by dt, and then it was negative sine theta, cosine theta, 0. Now, this is a scalar multiple of this vector. I'm going to use that property again, that I can take scalar multiples and I can just do the cross product of this vector and then multiply by that scalar. So that's going to be d theta by dt, and I'm going to then cross cosine theta, sine theta, 0 with negative sine theta, cosine theta, 0. So let's work out this cross product, and then we'll multiply it by this. That will give us this cross product, which will then multiply by r squared. There's a lot of bookkeeping involved in this. Okay, so if I want to just work out this cross product, that's going to be the symbolic determinant. We'll have I, j, k. Notice it is really important that we're actually working in 3 space so that I can work with the cross product. So even though my position vector is going to be on the xy plane, b is a multiple of k. It's not on the xy plane. Turns out its description is actually fairly important in this derivation, so I do need to be working in 3 space. So then I've got cosine theta, sine theta, 0, negative sine theta, cosine theta, 0. Okay, so if I work that out, I'm going to get some i's. The number of i's will be 0. Whoops, that was supposed to be a 0 there, I'm sorry. The number of i's will be 0 minus 0. That will be 0. I'm going to get some j's. The number of j's will be 0 minus 0. I'm going to get a 0 there. This shouldn't be surprising. I'm crossing 2 vectors that are in the xy plane, so I've got to get something that's mutually orthogonal to them. I'm going to get something that's a multiple of k. I also might remember, I might have forgotten, but I'm trying to calculate what b is. And we've already seen that b is a multiple of k. So this tells us we're on the right track. We're going to get a multiple of just k. So what goes here? Looks like it's going to be cosine squared minus a negative sine squared. But that's just cosine squared plus sine squared. Oh my goodness, that's just 1. So I'm getting k. U crossed with its derivative is just 0, 0, 1, or k. Very cool. So now, when I was calculating, I'm sorry, u crossed with its derivative is k times this. Don't want to forget I was scaling it by d theta by dt. Okay. So I'm going to get d theta by dt copies of k. Now let's see. That was this cross product. This cross product was the thing that we were multiplying by r squared. So now I can say this is going to be r squared times d theta by dt times k. And that was our second characterization of b. So we've said b is this multiple of k. It's also this multiple of k. So that gives me 2 different characterizations of exactly the same vector. And you'll notice this one, we're bringing in our r's and a little bit our thetas. We don't have theta directly. We have the derivative of theta with respect to t in this particular case. All right.